Hello, everybody. Welcome to the Activate Virtual Conference on Search and Artificial Intelligence. My name is Kevin Waters, founder of KMW Technology, and with me is Dan Fox, one of our principal search engineers here. What we want to talk about today is one of the contributions that we made back as a result of an engagement we had with LucidWorks with one of their clients to create, for the first time, the ability to do true large-scale joins and filters based on joins in Solr. So this is the talk on cross-collection join. A quick little introduction about who we are. So KMW Technology is a search professional services and consulting firm based in the Boston area. We primarily focus on Solr, Lucene, Elastic, Deep Learning for J, and many other open source projects. We perform Solr audits and upgrades. We do search application development where we perform relevancy and performance tuning, sizing, and we also create quite a bit of custom connectors and document processing pipelines, and even implement a large number of custom security models for customers who want that. So let's talk about how we got here. We had a customer, a very specific analytics problem. They had some very large collections. One of them was about 50 million documents across 5 or 10 shards, and the other one was about 1.4 billion documents across, I think it was 140 shards. Very large scale records. Each of the individual records themselves were relatively small. And similar in a way to like an IoT sort of data set. But rather than talking about that customer in particular, we're going to use an example that we came up with that shows the fundamentals of this capability using a customers and orders sort of example set. But obviously, whatever your application is, you'll see if you can apply this to your your own use cases. So some of the key things is that in one collection, they had records about customers, for example, that were very fat records, very wide, they had a lot of metadata on them, and the client wanted to be able to do ad hoc queries to look at a subset of those customers and then do analytics on the orders that those customers were generating. So the ultimate solution that we came up with for this was the cross-collection join query. And we'll talk about that now. So here's just an example of the use case, the example use case that we're talking about in this slide deck, where we have customers. You can imagine a customer has an ID, a name, street, address, city, state, phone number, really any metadata you could imagine putting on a customer record. And it had order records that again, had things like quantity, payment method, total amount, etc. And the key thing here is that both of these had a customer ID, and this is fundamentally where the joins would be executed across. So for this, we should probably update this. Actually, these numbers are a little bit off, but for the example we have, we actually built a test index of 100 million customer records and about 1 billion orders for our test cases here. And generally speaking, you can do analytics queries on either side of it, right? You could do one query against the customer's collection for all the customers in San Francisco. If you wanted, you could fast it on their birthday. Or you could do a query against the orders collection for a particular time range, and maybe you want to get like the total value of all of their orders in a particular time range. But the problem is being able to combine these two queries, right? Only customers from San Francisco or only customers from Kansas City, for example, and then just looking at those orders. And the real problem is that the metadata that you want to filter on is in one collection, the customer's collection, and the data that you want to do your analytics on is in a separate collection, the orders collection. So there are a couple different approaches to this problem that have been historically used in the Solr and search communities. One approach is to denormalize your data and flatten it, right? Where you take the metadata from the customer records and you put that on the orders records. Well, this approach has some pros and cons. One pro for this is that it's supported with simple term queries if you flatten your data. But the very practical con is that when you're flattening all the metadata of your customers, that the size of the resulting index would just be blown out of the water because the ratio between customer data to order data it's a very high cardinality set. And when you flatten all that metadata, the index size would just be prohibitively large. I mean, multiple terabytes. One other drawback to this approach is that a change to a customer attribute will trigger a need to do a massive amount of re-indexing in many cases, which from a processing perspective is also prohibitive. The second approach would be to use the existing join query parser, which is, could do this, where you can use the join from one core to the collection that you're searching on and do those statistics. The pro for this is that it's supported with the standard join query parser. Another pro is that, because you're not denormalizing your documents, you don't have to actually re-index them. Re-index all of the data that you've denormalized onto the order records. So you got one big benefit in terms of indexing there, but one of the drawbacks is that it requires that the collection that you're joining to, or the core that you're joining to, has to be co-located on the same node. So if you've got 22 servers, it would mean that you would have to have 22 copies of your customer's collection. The customer's collection in itself, is half a terabyte. Scaling that up is again very prohibitive. And one of the other things that's a major sort of drawback in this approach is that if any one of the replicas of that customer data was offline or in recovery for whatever reason, then queries to that node would actually fail because the shard that they would, or the core that they want to join to, was not necessarily active. So another approach that we came up with was to actually co-locate the customer documents in the same index as the order documents. And one of the pros is that this is supported by the current join query parser, and it does not require any re-indexing or of the data because the metadata hasn't been denormalized. But one of the drawbacks is that the indexing logic is a bit more complicated because the documents need to be routed to the same shard based on their customer ID, because you can only join to documents that are in the same shard. Joining on other fields is prohibitive because potentially you need to completely redesign how you're routing your data in the index. You might have to re-index or build an entirely new index to support joining on a different field, which would be problematic. And this kind of shows that this would limit the ability to do ad hoc queries between these collections. So the approach that we finalized on was actually just biting the bullet and going down the path of looking at what it means to actually do a full distributed join in Solr. And there are many iterations that led us to the final solution, which is contributed back now into Solr, that had, various problems and scaling issues along the way. And I believe that we've addressed many, if not most of those concerns with the final solution. So a couple things that we wanted to keep in mind when we were doing this distributed join is that we created a custom query. And that custom query actually executes a streaming expression against a remote collection. And that streaming expression returns only the keys that could possibly match on the local shard. We'll get into more detail about that. And some other things we wanted to make sure that we did is don't keep a large number of join keys in memory at any given time. So we ended up creating a join key collector that as the join keys are coming back from the streaming expression, it's looking at the term enum, and it's actually updating a fixed bit set representing all of the documents matching locally for those keys. One of the nice things about these fixed bit sets is that they're very easily cacheable, so that result set can be stuffed in the standard Solr filter cache. And we extended it a bit to support a time to live on those filter cache entries. One of the issues that we had to deal with is that the customer's collection could potentially change or be committed at a different interval from the orders collection. So we needed some way to expire the cached result set. And we achieved that with a TTL parameter, a time to live. So streaming expressions are an abstraction that kind of sits on top of the Solr's export handler. And the export handler is really, really efficient. It works by running a search. You have to specify a sort on a particular field. And the fields that you're going to be returning with the export handler or streaming expressions need to have doc values equals true. Luckily, this was the situation that we had. One of the beautiful things about streaming expressions is that it's extremely fast for returning the data back, potentially up to 400,000 join keys per second are coming back from a single node in our practical experience. One of the nice things about streaming expressions is then you can decorate the result set and do some post-processing on what's coming back. So the streaming expressions allows us to wrap the underlying search against the customer's collection in a unique operator to ensure that we're only returning unique join keys. This avoids excessive network transport time for doing these operations. As we'll see later on in the slides, actually, the network tends to be the bottleneck for a lot of these large-scale join operations. So the cross-collection join query, the initial version of it was called XCJF, cross-collection join filter, because it really is more of a filtering operation that allows you to search your primary result set filtered down by some join keys that are fetched from a remote set. So it's been integrated with the existing join query parser, where you can specify the name of the collection in the from index, which can be a remote index now, and that will be queried for the join keys. There are no specific document routing requirements for the remote index. They can be sharded or single shard, however you want. There's no specific requirements around that other than doc values is true on the join key field that you're going to be fetching. In order to scale up the concurrency of the system, you can add replicas to the remote collection. And this will allow multiple shards to be able to query in parallel against that remote collection. And if the local index, if you have the ability to route the local index by the join key, you can take advantage of a massive optimization that we added into it. We'll talk more about that in just a little bit. So here's an example of the query syntax where we have a join. The method is cross collection from the customer's index on the customer ID field, searching for just the customers in San Francisco, for example. And you'll notice that this was done as an FQ or a filter query parameter. And what the filter query parameter does is going to give us the filter cache entry that we're going to want to reuse. Because remember, the base use case for this was for generating analytics dashboards that were looking at subsets of cohorts, subsets of populations, and doing analytics on their orders and actions. So the ability to cache the result from this join to the other collection is highly desirable, and you want to execute this as a filter query if you can. So one of the things that we did talk about a little bit is that we did a number of optimizations to this, but one of the most fundamental and important ones is one that allows the number of shards to increase in your local collection without increasing the number of join keys that have to go across the network. So if every shard had to fetch every single key in order to ensure from the remote collection, then the total number of keys exchanged over the network would be the total number of keys involved in the join times the number of shards. And that grows very quickly. And it gets to the point where it'll just be prohibitively large amount of data that needs to transfer over the network. So one of the additional query parsers that was introduced as part of this pull request is the hash range query. And the hash range query allows you to query a remote collection or query a collection, but only return the documents who have a field value that would hash to a particular range. And let's talk about why that's important, right? In your local collection that you're searching with the join query, you have multiple shards, and each shard is going to be assigned a range. And this range is the range of the hashed value used for routing. So typically it's the document ID, but you can route on a different field, for example, like customer ID, if you have the flexibility to do that. And what the Solr internally uses the Murmur3 algorithm for this hashing. So effectively what we have now is a query parser which allows us to query the customer's collection, but only return the customers whose customer ID would hash into the same range as one of the shards in the local collection. This means that every shard in the local collection can run the query with an additional filter, and that filter is a hash range query filter to only return the documents that would potentially join to that local collection. This means that as you increase the number of shards, the total number of keys that are exchanged across the network remains constant. And that's a very important thing. So in the example that we have here, you can use the routing prefixes and the composite ID router. This might look familiar to some of the people out there that have done this, and there's large Solr clusters where effectively you take in our case, the customer ID field, and you prefix it on the document ID with an exclamation point. And this tells the composite ID router in Solr to send this document to a specific shard in the collection. So the syntax for this hash range query parser is just hash range. You tell it which field you want, and then you have a lower and an upper bound for the hash range. And this basically this runs a query. Internally, the hash range query parser has a cache, which is configured on a per field basis in the Solr config. And what this cache does is it goes in, it's a per segment cache, and it goes in and it pre-computes all of the hash values for the customer ID and stores those for quick lookup to do these range searches. And then when this query comes in, it's simply doing a range search on that cache in order to return the documents that actually match just that set. There is a slight cold start problem that cache needs to be generated. And you can either pay the hit on that up front, or you can just do a simple auto warming query. Any auto warming query, any hash range against the particular field will trigger that cache being created. So here's an example on the lower part of the slide. You can see that the cache has this prefix hash underscore and the field name, has a size, no operator generator. And this is all you need to do in your Solr config XML for the remote collection that you're going to be searching against. On the local collection that you're searching against, just as some syntactic sugar, you can override the default definition of the join query parser and specify the field that your documents are routed by in your local collection. In our case, that's the customer ID field. And what this means is that at query time, when you run a search, if you are doing a join on the customer ID field, the query parser will be smart enough to enable this routed equals true optimization for you. So let's just talk a little bit about performance, and we'll get into some more details. But we set up a 5-node cluster in Amazon using compute optimized C5D 2x large. We created 2 collections. One is a customer collection of 100 million documents across 5 shards, and an orders collection, which is 1 billion documents across 50 shards. In order to do the hash range query, the initial query to generate all those hash codes in the cache on that side, that one query took about 3.5 seconds. At that point, it's totally cached, and then it's fine. Now, here's one of the interesting things. We want to see the worst case scenario. And the worst case scenario is when you're joining all billion order records to all 100 million customers. And executing this query on these 5 nodes took 38 seconds. Now, prior to adding the hash range optimization, it took like 40 minutes. So this is a very, very significant improvement in terms of performance. But most people don't need to actually join on, all 100 million unique join keys. Rather, they can look at a subset of those. So we looked at a more practical example where in our example here, we ran a query. I think it was for all customers in California or something. This roughly returned about 2.8 million unique customer IDs. And what we did without the hash range filter optimization took about 47 seconds. But as soon as we used the hash range filter optimization, these queries, which are joining a billion records to 100 million customer records, filtered down to just about 2.8 million of those customers, returned in about a second. So the interesting thing here, in the 1 billion document collection, we had 50 shards. Previously, without the hash range, it means that 50 copies of the join keys would have to go across the network. With the hash range query, only 1 copy of the join keys goes across the network. And as a result, you see nearly a 50x improvement in performance. One of the neat things that we did is we actually looked at, what does performance of this look like at scale? And it's really driven by the number of unique join keys that are going to be participating in the query, and it's roughly linear. So in terms of search response time, anywhere under about 2.5 million unique join keys, your queries are going to come back. Uncached queries will come back in roughly less than a second, which is pretty impressive. At least I think it is. I was kind of blown away by these numbers when we were looking at them. So it's a couple little last details. The TTL and cache consistency. As we know that if we're querying the orders collection, it has no idea that the customer's collection may have been updated. So one of the things that you can specify as a local param for the join query parser is the time to live. And that means that this cache entry will be valid for, by default, up to 1 hour. So, assuming your customer's collection hasn't changed, this TTL is going to kick in after an hour, and it will force that re-execution. Should you want to use it, it is there, but it defaults to 1 hour, and it's important to be aware of that it's there. So a couple of details on the availability of this. This was committed as part of Solr 13749 by Gus Heck, and Dave Smiley had quite a few bits of feedback and a lot of guidance to help us make something that hopefully the Solr community will use and benefit from for years to come. This was committed to the 8.6 branch on 6/25 and is part of the Solr 8.6 release. So we encourage you to try it out and let us know what you think. I say thank you very much for your time today, and we look forward to hearing how people are using this out in the wild.